Hello. So today we're going to be looking at practical applications of logarithms. So we've seen that the log function is often useful when answering questions about exponential models because logarithms undo exponentials, right? Because we know that the log is the inverse of the exponential function. So logs are going to be a very useful tool in order to solve exponential equations, specifically when you're trying to find the exponent. So we've sort of seen examples of this before where previously, if you were trying to find x and you knew the y, that was something that you had to use a calculator to do and use a graph because you were not sure how to algebraically solve it. So now that we have logs, we now can algebraically solve it. So in this lesson, we're going to look at a bunch of different examples of some real-world applications for where you would use logs in order to solve. So let's look at this first one, which is just a simple population model. So the US population in millions is currently growing according to the formula. P equals 299 times 1.009 to the t, where t is in years since 2006. And one is the population predicted to reach 350 million. So to solve this problem, you're going to want to sub in 350, because remember it's in millions, for the population. And so you would end up with 350 is equal to 299 times 1.009 to the t. And so this is exactly the kind of question where before you would have to use a graph to solve it. And we can actually check with that. So let's quickly look at what a graph of this would look like so we know what it should be, and then we'll look at how we would do it with logs. Okay, so I did a quick graph of these in Desmos, and as we can see from our previous life, the way we would have found it is to put the y value we wanted in the equation y equals 350, and then we would have graphed our equation y equals 299 times 1.009 to the x, and then we would have looked for where they intersect, right? And so that tells us that we would reach a population of 350 million about 17 and a half years after 2006. So let's look at how we would do this algebraically. So if I was going to solve this algebraically, we're trying to isolate t. So the first thing I'm going to do is divide both sides by 299. And so then I'm going to plug that into my calculator, and I get approximately 1.171. And again, I'm going to shorthand it in terms of writing it, but when I'm using my calculator, I'm going to grow up and grab the full value so that I'm not rounding until the end. Okay, so now this is the point where I'm now trying to solve for the exponent. And as we mentioned before, this is something that we weren't previously able to do. But now that we know about logs, we can convert this into log form. And again, remember, we always start with the base of the exponent or the log, and then do our little circle, right? So this is going to be log base 1.009 of 171 equals t. So then we can plug in this log base 1.009 of 1.171 into our calculator to get for t. And again, remember, if you don't have a calculator that has a different base, we would plug this in as log of 1.171 over log of 1.009. And so either way, when I go into my calculator, I get that t should be 17.577, which, if you'll notice, is exactly what you got when you did it graphically as well. So that is how you would solve it with logarithms rather than needing to use use a graphing utility. Okay, so what that means is when is the population predicted to reach 350 million? It is going to be 17.577 years after 2006, which is during the year 2023. So about halfway through 2023. Okay, so let's look at another example. So in this one, we're going to buy a laptop for $1,250, and its value is going to be decreasing at a rate of 30% each year. So first we want to write an equation relating v, the value of the laptop, as a function of n, the number of years since it was purchased. So this is going to be an exponential because it's decreasing at a consistent rate. And so we're going to have our starting value of $1,250. If we are losing 30% a year, remember that our B value is always what am I keeping? So I am keeping 70%, so 0.70, and raise it to the n, the number of years. So that would be our equation that's exponential. And so if I wanted to find its values 2 years after purchase, that's easy because I'm just going to plug in 2 for n. So my value is going to be 1,250 times 0.70 to the 2. And when I plug that into my calculator, I get that that's 612.5. So it's going to be only worth $612.50 after 2 years. And again, like most laptops usually are about 3 years is kind of the reliable lifespan of tech. So it's not really surprising that the value is pretty low after 2 years. So then the next question is how many years since its purchase until the computer is only worth $100? So this is where we're now going to need to use logarithms because now I know that my value, I want to know when it's 100. And so this is where I'm trying to solve for my exponent. And when I need to solve for my exponent, the way I get that down is using logarithms. So again, first I'm going to start isolating. So I'm going to divide both sides by 1250. And so then I'm going to get 0.08 is equal to 0.70 to the n. And to get this into log form, again, remember I'm always going to start with the base and then do my circle. So this would be log base 0.70 of 0.08 equals, and then back up to the exponent equals n. And I can plug that into my calculator. Again, if I don't have a calculator that has different bases, I would type this in as log of 0.08 divided by log of 0.70 using change of base. And either way, when I do this, I'm going to get that n is equal to 7.08, meaning that it takes about 7 years. So how many years since its purchase is it only worth $100? About 7 years. So about 7 years to get value down to $100. Okay, so our next example here is going to talk about doubling time. So eventually any exponential growing quantity is going to double or increase by 100%. Since its percent growth rate is constant, the time it takes for the quantity to grow by 100% is also constant. This time period is called the doubling time, right? So in short, doubling time is how long does it take for a quantity to double. So to find the time needed for the turtle population described in the function p equals 175 times 1.145 to the t to double in its initial size. So in order to do that, we would want to look at our starting value, which is 175. And so in order for it to double, so there's a couple ways of doing this. You can either think about actually finding the double, right? So 175 times 2 would be really asking, like, when is the population 350, right? And you could plug it in like this, right? Or you could also say, well, really what I want to know, it doesn't matter what my initial population is. I want to know when my population is twice whatever that initial population was. And so you can say, well, really, how many times do I need to multiply by my growth factor of 1.145? Like, how many times do I need to multiply that to have it be the equivalent of multiplying by 2? In other words, doubling, right? And the reason why you can think about it either way is that if I did this first way here, where I actually just found double the population, if I started to solve for t, the very first thing I would do is divide both sides by 175, and because we figured out what 175 doubled is 350, that's always going to be 2, right? Because the way you found it was by doubling the initial population. So you end up exactly at the same spot eventually, depending on which way. So it's just a matter of which way you like to think about it. So again, you can either think about what is my initial population, multiplying by that by 2, and then substituting that in for the population you're looking for when it reaches. Or you can say, okay, it doesn't matter what I start with. What I really care about is what does this quantity, what is 1.145 to the t, what does t need to be in order for that to be equivalent to multiplying by 2 so that it's doubled? So now we can go ahead and use logs to solve this for t. So we would get log base. So again, remember you're always going to start with the base of the exponent and then circle around. So log base 1.145 of 2 equals t. And we're going to plug that into our calculator, and we should get that t equals 5.119. So that means that it's going to take a little over 5 years for the turtle population to double. So it takes 5.119 years for the turtle population to double. Okay, let's look at another example. So now it says a population doubles in size every 20 years. What is its growth rate? So now we're going to set this up again. Remember, this is going to be exponential. So y equals ab to the x. So if I know that it takes 20 years for my population to double, really what I know is that for y divided by a to be the equivalent of 2, right? Because if it's going to double, y would need to be twice as big as a. So y divided by a is going to be 2. So 2 equals b to the x, and we know that it took 20 years for it to double. So you can set up the equation that 2 is equivalent to whatever the growth rate is multiplied by itself 20 times, because it took 20 years for the effect of multiplying by 2. And so to solve this one, you can either think of taking the 20th root of both sides, so you can take the 20th root of 2 to get b, or of course you can think about raising it to the 1 over 20 power, so b could also be 2 to the 1 over 20. So then we're going to plug that into our calculator, and we get that b should be equal to 1.035, which means that the growth rate is that it's growing by 3.5% yearly. So it's growing 3.5% yearly. Okay, let's look at an example. So similarly to the idea that you can have a doubling time, you can also have a half-life or a decaying time. And half-life is actually how they do a lot of carbon dating, where they're looking at the decay of carbon over time. So if you know the rate at which a certain element should be decaying, that can help you date and figure out how long something's been decaying for, which is helpful in dating a lot of various things that you might find in like an archaeological dig or something like that. So just as before we were trying to figure out the equivalent of when am I doubling or multiplying by 2, now I want to say, well, when it's the equivalent of multiplying by half. So carbon-14 decays radioactively at a constant annual rate of 0.0121%. Show that the half-life of carbon-14 is about 5,728 years. So essentially what we're saying here is that if my decay factor, so again, if I'm losing 0.0121%, I'm going to do 1 minus 0.00012, right? Because again, I'm going to move my decimal, right? So that would be 0.0121% in decimal form. Neaten this up a little bit. Okay. All right, so when I do that, I'm going to get 0.99988, meaning that I am keeping 99.988%, and I'm losing the rest. And so what we want to see here is that if I'm multiplying by 0.99988, what we want to say, so it told us that the half-life was 5,728 years, and if this is correct, if we do this out, it should be the equivalent of 0.5, or multiplying by half, right? So this should be, is it equal? Let's find out. So if we do this out, we get that 0.99988 to the 5,728th power is 0.500009. So very close to 0.5. So yes, that is in fact close to the half-life. All right, let's look at another example. So another place where we see logarithms a lot are when we are measuring quantities whose magnitudes are very widely. So things that this happens a lot with is acidity, so pH, right? So if you think about how acidic something is, what their pH is, as well as sound in decibels, or earthquakes, which the Richter scale, when you say it's like a 7.0 earthquake, that is actually a log scale. So in chemistry, the acidity of a liquid is expressed using pH. The acidity depends on the hydrogen ion concentration in the liquid in moles per liter. This concentration is written as H+, and the greater the hydrogen ion concentration, the more acidic the solution, and the pH is defined by the negative log of the hydrogen ion concentration. So again, just a note, don't worry, you don't have to memorize what pH is. That is something that you would have on your test given to you. So in this example, it says the hydrogen ion concentration of seawater, H+, is 1.1 times 10 to the negative 8th, and we want to estimate the pH of seawater. So in order to do that, to get our pH, we need to take the negative log of the hydrogen ion concentration, which is 1.1 times 10 to the negative 8th. And so we're going to go ahead and plug that into our calculator, and we should get that the pH is 7.9586, which is not surprising that it's not terribly, oh, actually 6.1. So it is not terribly strong pH. So remember, keep in mind that like regular water or neutral pH would be 7, so 7.95861 is slightly basic, but not by much. So if you haven't seen pH before in science class, so 7 is neutral, and then as you get larger numbers, then it is going to be basic, and if you have smaller numbers than 7, it's acidic. Okay, let's look at another example. So now, if I have a vinegar solution and it has a pH of 3, determine the hydrogen ion concentration. So if I know my pH is 3, then I can find my hydrogen ion concentration by using log. So again, remember it's log base 10. So if I wanted to convert this, you could think about sort of the little phantom 10. And before I convert this, first I need to get rid of this negative out front here. So I'm going to divide both sides by -1. And so I'd have -3 equals log base 10 of the hydrogen ion concentration. And so now to convert, remember we're always going to start with the base of the log and then do our little circle. So we're going to have 10 to the -3 equals our hydrogen ion concentration. And so 10 to the -3 is going to be 1 over 10 to the 3rd, which is going to be 1 over 1,000. So our hydrogen ion concentration of vinegar would be 1 over 1,000. Okay, let's do an example. So if one object is 10 times heavier than another, we say it is an order of magnitude heavier. So if one quantity is 2 factors of 10 greater than another, we'd say it's 2 orders of magnitude greater, and so on. So for example, the value of a dollar is 2 orders of magnitude greater than the value of a penny, because we have a dollar divided by 1 cent would be 100, or 10 squared. So the order of magnitude is the logarithm of their ratio. So if you took the log of the larger quantity over the smaller quantity, that is going to give you the order of magnitude. Because remember, if you're doing that, you're saying really it's 10 to the what gives you that ratio, right? So it was 10 to the 2 that gave us that ratio of 1 over 0.1. So that's another place where we see logs. So the sound intensity of a refrigerator monitor is 10 to the negative 11 watts per centimeter squared. A typical school cafeteria has a sound intensity of 10 to the negative 8 watts per centimeter squared. How many orders of magnitude more intense is the sound of the cafeteria? So again, we're going to put the larger quantity on top. So 10 to the negative 8 over 10 to the negative 11. And we take the log of that quantity. And so when I do that, I would have 10 to the negative 8 minus negative 11. So this is going to reduce to log of 10 to the positive 3. And so 10 to the, if we wanted to set that equal to x, we could say 10 to the what is equal to 10 to the 3. So x would be 3. Meaning that the order of magnitude is 3 times, right? So it is going to be, the sound is 3 times more intense in the cafeteria than it is from listening to the refrigerator motor. Okay, so the intensity of audible sound varies over an enormous range. The range is so enormous that we consider the logarithm of its sound intensity. This is the idea behind the decimal, abbreviated D capital B. To measure sound in decimals, the sound intensity is compared to the intensity of a standard benchmark sound, which is I sub 0. The intensity of I sub 0 is defined to be 10 to the negative 16 watts per centimeter squared, roughly the lowest intensity audible to humans. So the comparison between a sound intensity I and the benchmark sound intensity I sub 0 is made by saying that the noise level in decimals is equal to 10 times the log of the, so remember that the log of this sort of ratio, where the larger or the louder thing, right, because assuming if 10 to the negative 16 is kind of like the lowest audible sound, right, so the sound intensity I that you're looking at is going to be the louder sound. And so the log of this would give you the like order of magnitude for which one is stronger. And so then we multiply that quantity by 10, and that converts it to decibels. So it's just a unit and a way of talking about sound in a way that you can easily compare. So let's do some examples with that. So we've got this up here just to remind us that the noise level in decibels comes from doing 10 times the order of magnitude. So the noise level of a whisper is 30 decibels, and so we want to figure out how intense a whisper is. So if the noise level is 30 decibels, then we've got 10 times the log of whatever that intensity is over 10 to the negative 16. And so first thing we would do is divide both sides by 10. So we've got 3 equals log of I over 10 to the negative 16. And so then we're now going to convert so that we can solve. Remember, we've got kind of our phantom 10. We always start with the base of the log and then do our little circle. So we're going to have 10 to the 3 equals I over 10 to the negative 16. And then we can multiply both sides by 10 to the negative 16. And now we've got 2 with the same base. so I is going to be, they've got the same base, so we can add them. So we've got negative 16 plus 3 is going to be 10 to the negative 13. And so that means that the noise level of a whisper is 10 to the negative 13, right? Which makes sense because a whisper would be quite low, right? You wouldn't expect a whisper to be very high. And so 10 to the negative 13 is not significantly higher than 10 to the negative 16. All right. So that is it, and now you've got some homework problems to practice this. So hopefully that helped you give you an example of times and places that you see logs being used in the real world.